All right then. Well, welcome to another exciting embedded microcontrollers class. I found this little cheat sheet online and I thought it was kind of an interesting thing. Um, it has the look and feel of kind of like a nice summary of all the kinds of things you might like to commonly do. It shows you how to establish constants. Has this little thing in here about data types, the common data types. And then this little guy in here about strings, that looks kind of interesting. Let's see now. We've seen bitwise operators before. Compound iterators, I think we've kind of covered those pretty good. You might actually have seen a lot of this syntax in your CS131 class, but probably didn't see the define and the include syntax, but that's part of the macros that we had been discussing. There's this nice thing in here about control structures and summary in case you forget like how to use a switch statement. But that is the same switch statement that you'll see in Java. I mean, that's a CS131 thing that you probably covered before. You may not remember it, but it was there. GoTo, I think, is reserved, and I don't think people use GoTo anymore. Let's see now. What else is in here that looks interesting? Oh, program memory. This is when you get to write directly to the flash. You have to use that with some care. If you do it too much, you'll wear the flash out. And let's see what else is cool. We've seen pin modes being used, like you put in a pin like 9 and you write output and sets it up as output. I'm just going to mute you, John, because you're coming through. And then it says analog I/O. We've done that. We've done some nice reading from the input and the output. Let's see now. Time delay. We've done time delay, but we didn't do it in microseconds. It's nice to know you can do that. You can get the actual time since the machine has been booted in either milliseconds or microseconds. Don't know how accurate that stuff is going to be when you go to microseconds. I wouldn't trust it, but you know, you can certainly use it to benchmark your programs. Let's see now. This stuff, bit setting, bit clearing, that's actually very useful. Setting and clearing an individual bit is so important. And I'm going to talk a little bit more about that in as the lecture proceeds. Is everybody muted? I heard echo in here. Just make sure you're muted. And then let's see what else is going on here with this couple of other things. External interrupts. We kind of alluded to that a little bit. The libraries for serial, you can see the common baud rates. Just pull up your monitor on the Arduino IDE and you'll see baud rates that are permitted. I'll launch mine just for fun so we can see it. And while that's running, I'll continue. This little thing in here, double EEPROM, include the double EEPROM, do a byte read, do a byte write. That's really Arduino specific stuff. You may not be doing that anytime real soon, but it's good if you want to take a parameter and read or write it to the double EEPROM. And let's see now, what do we got here? Serial begin and read. We haven't done any serial reads yet, and we're going to do that pretty soon. And let's see what else. The wire we haven't touched on at all. We didn't do anything with the random number generator. Sine, cosine, tangent, we can talk about that a little bit today. And that's about everything that we've covered so far. There are a few things in here, like analog reference. We'll have to cover that in some more detail, and we will do that. So that's a that's sort of an interesting little summary sheet. I kind of liked it because it had all this interesting Arduino stuff in it, as well as some general stuff that you might like to sort of refer to. And then in the upper right, you can see your Atmega 328. That's your Uno, and he tells you got a K byte of double EEPROM, 2 K bytes of static RAM, and 32 K bytes of flash loader. That's actually where the gist of this the storage is on the ATmega is in your flash loader, 32 K bytes. So not a lot, right? I mean, very limited stuff going on here, but it's nice to see someone has created this reference and you can use it at will as you like. And as far as knowing what the correct baud rates are that you are permitted to use, go to your serial monitor. And it's not available because it's not plugged in. Let's fix that right now. Let's see if we have a port. And I do. I have a port. So here's my CHU340G. And now I should be able to bring in a serial monitor. And sure enough, you can see it's actually running a program and its output start at 9600 baud. But these are the common baud rates. Anything over 115,200 for this Arduino is going to be unreliable. It just can't keep up. So after 115 kilobaud, if it works at all, it'll be intermittent, I think. And then what I did was I wrote a little program, and this is going to be something we really ought to think about studying a little bit. This is a program. Let me sort of just see if I can upload it. So here's a way to initialize a sine wave, right? So this is now we're dealing with an MCP 4921 12-bit digital to analog converter with an SPI interface. And what we want to do is create a 12-bit wavetable. And with 12 bits, we want to go from 0. I can probably put a note in here on that. You want data to range from 0 to 4096. Right. So what we know is that sine ranges from -1 to +1. That we know. And so 1 plus sine ranges from 0 to 2. And therefore, 2040 times 2 is 4080, which is a little lower than 4096. So 2 times 2040 is equal to 4080, which is a little bit less than the top end, 4096. In fact, you could only go to 4095 because you start at 0. So when it says 4096, it's not quite right. It should say 4095. And that gives you a little extra headroom. And so that's where we're getting this number from right in through here. And then for theta, we're using a delta theta. And delta theta is a function of n, where n is the total number of samples in the wavetable. So if you go back to the top, here I've established n as being 128 samples. And so then I said my delta theta, if it ranges from 0 to 2 pi, must go in increments of 2 times pi divided by n. And so that gives me some sort of a number. And in fact, if you wanted to, I'll get a calculator and I'll do this, all right? So 2 times 3.14 divided by 128 gives me 0.049 radians. If I divide that by 3.14 and then multiply by 180, I get it in degrees, and it's 2.8 degree increment. So it's a pretty small increment, but not infinitesimal. It's not really epsilon, Anyway, we go through and we create that sine wave, upload the whole thing to our little Arduino, and take note of the fact that we've got a little DAC write function in here. And that's actually going to output, we'll just say this right here, output to the MCP 4921 SPI 12-bit DAC, right? That's what that does. And what you do is you see the output buffer coming in, and we grab 1 byte at a time, W bytes, takes this output buffer and turns it into a little array, and we get the most significant and least significant bytes of the array, chug them out to the output buffer, and take the output buffer, break it up, and write it out, and the rest is just sort of the transfer. Here's my loop, and so my loop has this index that keeps incrementing, and if the index is going forward by dx, where dx is equal to this value that comes in off the potentiometer divided by 32, one thing I can tell you about the value ranges from 0 to 1023. And therefore, val divided by 32 ranges from whatever 1023 divided by 32 is. I'll tell you in a second. 32 is 32. 0 to 32. So that's quite coarse, right? And so that'll be 0, 1, 2, 3, 4, 5, 6, all the way up to 32. When you do 32, you're skipping a lot of samples. And that's going to guard the input, right? We're guarding the input because we don't want to go off the end of the array. So if the index is greater than or equal to n, total length of the sign table, we'll reset it to 0. And then we'll just do the DAC right, and that's the loop. I mean, you can do this with interrupts. You can make it as fancy as you want, but I'm not going to do that. This is fine the way it is, I think. In fact, I had it all set up with interrupts, and I said, what am I doing this for? I don't even need it. So the rest of this is boilerplate. Chip select has to be set for output. You have to pull the LDAC input to high and low, and we'll show why in a second when we look at the data sheet. And then we have to do the rest is SPI mucking about. So let's see if we can upload this thing. Here's the advantage of teaching from home without being in the classroom, because I couldn't have done this in the classroom. And now he's done uploading. And now I think maybe I can turn on my speaker, and we'll see if we can get this to work. So that sort of works. And that's kind of where we're going with the lab. You know, it's an interesting idea that you can try and do these things in hardware, and it's relatively simple to do when you have the code. And so what we'll do is we'll have a nice little lab this Wednesday, which will explore how to use the MCP 4921. But one of the things I kind of thought might make sense for us to do is to take a quick look at the actual data sheet. So here is the MCP data sheet, and they've covered, you know, a variety of families. They have them in different flavors, 3 fantastic flavors, and there's the 8, 10, and 12-bit versions of these chips, and that's sort of interesting. I mean, that's nice to have. And then what you can see is he's got like this little DAC and an input register, and he's got some kind of interface logic, which I imagine is a shift register, and he takes a serial data input. He has his clock, which is going to shift the data in. He has this chip select, which will activate this from a tri-state to an active circuit. And basically, it's just a shift register that says, aha, I'm going to start listening to the clock and the data coming in. Once I have it, I'll figure out which input register it goes to, and then I'll flood my little DAC out, and then it'll make like voltage. And that's that. That's how it works. So I said, well, you know, that's not really very educational. Let's try and do it in Tinkercad, because what the heck? So I created this little video over here in Tinkercad, and I kind of think it's educational to watch it, but maybe it would be more educational to just like run the Tinkercad program. So when I go to Tinkercad, I've got my own little account in here with some circuits in it. And here's my little, I don't know, simulation of an R2 ladder network. And so with the R2 ladder DAC, I want to have an output, but I can't really hear it, so I use this oscilloscope to visualize it. And then I put in this little potentiometer to sequence through an 8-bit wavetable, because what I built with the R2 DAC is not really the same 12-bit table we had from before with our little MCP SPI DAC. Instead, what I did for this wavetable was I said, let's set up a wavetable for an 8-bit DAC. And so I did the delta theta again, still with 128 samples, but now I set them up as being bytes. If you look before, when we set up this wavetable, it was a little bit different, right? Because here's the sign table, and now it's unsigned integer 16-bit quantities. If you're going to have 12 bits, you can either have 8 bits or you can have 16 bits. You can't set 12 bits. You got to use 2 bytes. That's just the way it is with programming. They go in integral powers of 8 nowadays. PDP-8s used to have 12 bits, but those days are gone. And so if you go back here, you can see where I've got this set up with 8 outputs on a parallel output from the port over in here. And I'm going to set up this val again to input from the ADD converter. And I'll initialize my sine wave, but now here's sine again being adjusted from 0 to 2. So sine is ranging from -1 to +1. Sine +2 is ranging from 0 to 2. That's fine. And now we multiply by 120 times sine of theta +2. And now we've got a number which ranges from 0 to 240, which is less than 255. So I got myself a little headroom there, probably more than I need. And then for my delta theta, we already computed that. It's like a constant, and it doesn't change. It's just 2 pi divided by the total number of elements. And notice the total number of elements is also a constant, but you can change that as long as you have the RAM. Remember, RAM is quite limited. So then here's my serial begin. It hits start. Now here's the cool part. I set all of the output ports and the DDR-D register to 1, which means they're all going to be output. This is Boolean, binary number. And then I have my pin mode A0 as input. And I initialize my sine wave, and now I just do the loop as before. I know it's a little bit simpler. If I want to write out to port D, I just set it. Sine table is associated with port D. It's bytes, and then each one of the bits will be set. And now if you start the simulation, what you get is a sine wave, which is cool. And if you diddle the little knob, you should be able to change the frequency. And that's just so cool. Then there you go. So now you've got a simulation that is basically an R2 ladder with a wavetable and this little knob choosing what the increment will be through the loop that outputs from the wavetable. So once again, the analog read is changing dx, which is the increment into the wavetable, and that's what chooses what the frequency will be for the sine wave. There's no real sense of actual frequency because we don't know quite how fast this thing is running, and we're not really sure if it's giving us a frequency that we could estimate or measure or anything like this. Right? There's no, well, actually you could measure it, and let me show you how. Let's see. I think you can measure it, right? Because if you look at this, it says time per division 1 millisecond. Right? So if that's the case, if this is really real, that's really 1 millisecond, then in theory, you can look at this waveform here, and you can say, hey, wait a minute. Here's a trough, and there's a trough. This is 1 millisecond per division, so this is a little bit lower than a kilohertz, right? Because 1 millisecond is 1/1000th of a second, and so that's like a 1 kilohertz waveform. And there you have it, right? You've measured the frequency, such as it is. It's not a particularly reliable way because we don't quite know very much about how these things will really work. But, you know, there it is. The simulator has limits. The other problem with the simulator, and, you know, you can really pick away at these things if you like, it's doing an R2 network instead of an SPI, right? How do I do an SPI DAC on this simulator? And the answer is you can simulate an SPI DAC. Right? This is sort of bizarre and weird, but if you wanted to do that, then what you'd do is you'd get a shift register, and you'd shift out the data from the serial data out, and you'd use the clock to do the shifting, and then you take the shift register's output and run it through an R2 DAC, and then the shift register would act like a well, it would be a SPI DAC. That's essentially all an SPI DAC is a shift register with an R2 ladder. So that's a you know, a way in which you can simulate the SPI DAC if you chose to do that. I was kind of thinking about doing it, but I said, this is too much trouble by half. You'll spend more time trying to simulate these things than getting the hardware to work, is what I discovered. I was like, wow, the hardware's easy compared with the simulator. Why even bother with the simulator? Because, you know, you're not actually going to build this R2 network unless you really wanted to, I think. And certainly there's nothing wrong with wanting to do that. I've done it myself. It's educational. But having said that, DACs are pretty inexpensive, and why wouldn't you just buy a DAC, right? It's not, I mean, it's a good, I'll call it a good educational exercise, not a particularly practical one. Unless your goal is to learn how to build DACs, in which case, you know, that's fine. So that's a brief rundown of what we're going to be seeing for our next lab, and I thought you would like that. The other thing that I did was I created a little video that shows. Let's see if we can get this right. The SPI DAC with the sine table. And if you watch that, you'll see basically what I just ran through. I ran through the code for you, and this does that. And then you can hear what it sounds like. Just to kind of, not to put too fine a point on it, if you wanted to, you could probably take this code that's, you know, outputting these interesting and wonderful waveforms, and you could digitize it. And you might say, well, how would I do that, right? Well, there's all these applications for visualizing code. Or visualizing audio. I happen to have one called Audacity, and I've never run this program at the same time I've run Zoom. What could possibly go wrong? Yeah, right. So here comes Audacity, and what we'll do is we'll just sort of get some audio going here. And record it. And now what we'll do is we'll zoom in on it and see if it got anything. It doesn't look like much. Let's see if we can normalize it. I think there's a way to amplify these things. Maybe normalization is a better. I'm not convinced I've got the right input here. Let's just make sure we've got the right input. The input and built-in input is Samsung. Output is to recording. Hit OK. Let's see if we can. I think there's a nice way to normalize the. Oh, here it is. Normalize. So let's hit normalize. Hit OK. And there you go. Now we've got a signal which kind of looks like a sine wave. That looks very sine wave-like. Well, what happens if you play it? Well, hear that. So there, it plays it, it visualizes it, and you can modify it. And you know, whatever noise there is, it's almost certainly because I've amplified the heck out of it and recorded it with an open air microphone from a speaker in a noisy environment. So that's, you know, that's fair. And I like that sort of thing because it lets you visualize these things. In the lab, you can use apps for the iPad, or you can use Elvis, which has got a built-in software oscope, or you could use a real oscilloscope and hook it to the output, which is, you know, perfectly fine thing to do. And so that's a fun thing to do, and I find that very educational because it's giving you a nice hands-on signal processing experience. A couple things about this code, which is kind of interesting, I think. When you look at the code itself, you'll see there are a few bit manipulation kind of thingies that are going on. This will take a register and set one of the bits, or clear one of the bits. So CBI, here I'll put in a note, CBI of register 1 and then 4 clears bit 4 of register 1, whereas SBI register 1 bit 4 sets bit 4 of register 1. You could say, okay, well, that's, you know, that's kind of nice, but why do I care? It might be useful in comparison to doing something like, you know, R1 equals R1 inclusive or B7, 6, 5, 4, here's 4, oops, 4, 3, 2, 1. Right. That does the same thing. That will set. This sets register 1's bit 4, 2. But you can kind of see why, you know, one might be more notationally, let's say, nice than the other, unless your goal is to set a bunch of bits all at the same time, in which case you might be well more efficient to set like several bits at once and be done with it. So that's a that's kind of a little overview of what clear and set does. That's a built-in macro. Well, actually, this one's been defined for you right up in here, so that's kind of nice. And let's see what else we got. Anything else of any interest here? I think that's it. It kind of gives you a you know, a brief overview of how to use the SPI interface DAC, and I think that's a useful thing for people. I think people will want that. We'll do some more advanced programming in this area a little bit later on as the course progresses. Any questions? You can see we've got a few people here on tuning in, which is great. Thank you. You know, I'm doing this as an experiment from home just to see if you guys are okay with it, and you know, if you find it educational. If you'd rather be in the classroom doing this, fine. But I really like the idea of having a computer in front of me where I can do the programming and some hardware next to it. I mean, we don't have this in the classroom, and it would be a pain to set it up. So I kind of like having these resources. It just makes it nice, I think, me personally. So this coming Thursday, you've got a homework 5 due, Any questions about homework 5? I think I can bring in Blackboard here. Here is your microcontrollers course. And if we go to course content, we can see under homeworks. And here comes homework 5. And let's edit the options and make sure I'm right about the due dates and all. And yeah, sure enough, that's on the 8th. That's, well, today's the 5th, so that's going to be Thursday in the evening. So that's when that's going to be due. And so we have kind of covered this a little bit, but I'm happy to answer any questions you might have about question 5, homework 5.
Could we start off with question 7?
Sure. So let's take a look at I guess I have to go back to course content. I'm not sure why. Let's do homework. Take a look at begin, and then question number 7. So here's a what can the range be for the MCP 4921 DAC? So you've got 12 bits. So 2 to the 12 is something like 4096. And if you look at the range, including 0, it's 0 to 4095. So if I say here, what could the range be? And it says here it's 2 to the 0 to 2 to the 12 minus 1, which is 4095. That's good. Can you make it also so that it goes from 0 to 1023? And the answer is yes. Yeah, you could. Because why? Because you just need the least significant 10 bits. Or if you like, use the most significant 10 bits and ignore the rest. And then what about this 8? Can you do it with 8 bits? And the answer is yes. Just use the most significant 8 bits and ignore the rest. You know, set them to 0 if you like. So at some level, you could probably make it into a 1-bit DAC if you want. I mean, you can use as many bits as you like, up to but not exceeding 12 bits. So I would say any of the above is the analog range. What do you think of that? Is that?
Yeah, makes sense. Thank you.
Sure. Let me just adjust my. For some reason, Zoom is not using my headphones when you speak. I don't know why. And I'm afraid to change it, so I'm going to leave it alone. Any other questions about homework 5? I'll just sort of thumb through it here. Oh, here's that clear bit and set bit thing that we saw from before. Let's see now. I just started to thumb through it. Here's question 11. You guys stop me if you see something you want me to cover. Here comes question 13.
Can you cover 12?
Sure. Let's have a look. So here's something that says, according to this reference, SPI reference. You know, I like these references and being embedded in here because it probably means I can open something up and maybe it'll work. Oh yeah, there it goes. So here's like a little lesson on SPI. That's kind of nice. And oh, here's this stuff about SPI modes. And it chooses whether or not you're using rising or falling edges of clocks for something or other, transferring data. And it looks like, oh, this is very useful, right? Because now if you change from an Uno to a Mega or a Leo, maybe the pin numbers change. And this is very important if you're designing shields. And if you were going to design a shield, you might want to lay it out using using something like Eagle, which, you know, that's something I've been doing in the past. I was just thinking, yep, there it is. There's my shield. Eagle's an interesting thing because it's actually here's the chip right in through here, and you can see it's nicely labeled. And then if you go in over here, you can see where the pins are actually wired, and you can see how the different pin numbers have been dedicated to different SPI functions. And so what's going on, you know, with pins 9, 8, and 11 is probably something you could see with relative ease over in here, where he's saying for Uno, Mosi's 11, Miso's 12, so we skip it. It's kind of an interesting thing. You can see how these things map. So that's cool. And if you go back to Eagle, and this is, you know, maybe a little bit more detailed than you like, but it's kind of interesting if you're going to make your own boards. You can click in the upper left corner and switch to the schematic capture. And this maps directly to the board. So as these things change, the board layout will change and you'll have to redo the routing when you go to make your boards. So that's kind of a cool thing. In this class, we can actually design our own boards and have them fabricated if we want to get that far here in the class. It's kind of a fun thing to do, have the class design their own boards. And here you can see the serial clock, serial data in, chip select, and there's that LDAC that we were toggling before. And what you would do to learn how to use that is you'd read the data sheet on the MCP 4921, which is kind of neat. So it's interesting that you should ask that question because it gets you kind of deep into SPI and then how the actual DAC is working. So then he says, okay, we're going to use SPI mode 0. What does it mean, SPI mode 0? So we go back to this little lesson that we had from before. And I think there was this little thing in here about the SPI modes. Oh, and there it is. And it says clock polarity 0, clock phase 0, output edge is rising, data captured on the rising edge. So that's a rising edge data capture thing. So if you hunted down the actual link and you looked for that SPI mode 0 setting, you'd see we're actually using this first row in the mode table, and we're capturing data on a rising clock edge. And so when will the data be captured? Output edge is rising, and let's go back and take a look. Output edge is falling, data capture is rising. So falling and rising respectively sound like the correct answer for that. So you gotta, I mean, I guess what I was trying to do is I was trying to get you guys to follow along with this reference, and if you did that, the answer would become falling rising, which is just what you wanted to do. So I was hoping you guys would chase down the link and learn about things that way. What do you think? Does that sort of feel educational?
Yeah, it does. Just the reason I asked about it was because the options, I couldn't really know what they're talking about.
When falling and rising respectively, that means the output edge would be falling and the data edge would be rising, which is just the sort of terminology they use over here. Output edge falling, data edge rising.
Thank you.
Yeah. So that's kind of I was trying to give you guys sort of a lifelong learning experience, so you'd look things up. That sort of makes sense. Any questions about question 13? You guys are good with that? So here's one. I mean, here's set bit ADC SRA, right? And then he's saying ADP S30, ADPS2, ADPS1. What's that about? I don't understand that. What does this mean? What do you guys tell me? What is this? What is this prescaler? What is that? Any idea? What is he talking about, prescaler? So the prescaler is a register in the analog to digital converter. So let's if you ever have a question about this, type in ADCSRA. Use the Google. It's really good. I mean, it really is. And if you go in here, you'll see that there's a couple or 3 bits in the least significant bit register. Let's see if we can find the data sheets on this. Just a minute. There it is. Just missed it. There it is. ADSPS2, ADSPS1, and ADSPS0. So these are bits 0, 1, and 2 of the ADC-SRA. This is, here are the bits, and these are the division factors. So what this does is it says if you set all 3 bits to 1, it's going to divide the clock by 128. And if you set them to 128 division, you got to figure out what the system clock is. Now, for your Arduino Uno, your system clock is going to be 16 megahertz. And so if you take 16, let me do this with the calculator. 16, 1, 2, 3, 4, 5, 6, divide by 128, you get a number, 125 kilohertz. In other words, 16 million divided by 128 is 125K in kilohertz. Kilobytes would be something else. So then if you inverted it, that is to say, raise it to the -1 power, you get a number 8 times 10 to the -6, which is 8 microseconds. That is a period of time which is not equal to your sample rate, right? It sounds like it should be, but it isn't. This is not the sample rate. What this is, because it's a successive approximation ADD converter, is the clock that goes into the register for the conversion. So it's not quite your sample rate yet. It's the clock rate that goes into the ADD converter. So therein lies a true enough statement. 16 megahertz divided by 128 is equal to 125 kilohertz. And you now know how that is obtained. The question of how many clock cycles it takes, that's a different question. We haven't addressed it yet. But the first time you do this, it takes 25 clock cycles to do one conversion. So if you take 125 kilohertz and divide it by 25, I think it's like 5K. Yeah, that's 5. So in other words, if it takes 25 cycles first time through with a 125 kilohertz clock, it's going to be doing conversions at 5 kilohertz. That's pretty slow, actually. The second time through, it goes quite a bit faster, probably closer to the 13 clock cycles, which would bring you to a number of 9.6 kilohertz. The first time through, it'll be 5 kilohertz. It'll be slow. Here's one that says set bit PS2, clear bit PS1, clear bit PS0. That would give us an input clock of 1 megahertz. And let's see if that's true. So that would be, the input would be 100. And 100, that's divided by 16. And if you divide 16 megahertz by 16, you get 1 megahertz. So that sounds correct. And then the sample rate of 76.8 kilohertz, is that true? So take 1,000,000 and divide by 13 clock cycles. And what do you get is 76,923. What does he say? 76.8? That's pretty close. That's pretty close. So I'm getting all of the above. These all seem to work. And you know what's interesting about it is you kind of have to learn a lot about the A to D converter and the little bits that are being set. And now you can see why set bit and clear bit are so important, because what they're really doing is they're allowing you to change the sample rate of your A to D converter. And believe it or not, you got to go through the data sheets in order to be able to figure out how these things work. So there's a couple or three bits there that are kind of important. Here's one, ADEN, and if you read it, it says that's the enable. You better enable it if you want this thing to work, or it isn't going to work. So, you know, if you don't turn it on, what it does is it becomes just another input or output pin, and it'll be like a digital pin that you can assert or read from, a 1 or a 0. And then here's something called ADSC, and that starts the conversion. Well, you better tell it to start the conversion, or else it's not going to do anything. So this is the "it won't work if you don't do it" thing, right? You better toggle that bit, set it, and every time it's done, you got to set it again. You could do that interrupt driven. In fact, that's the way to do it, or you can do it some other way by calling ADC read, and that'll work too. There's this thing here called ADC free run, which will just let it convert as fast as it can, and you can just keep reading from the register. And so it does kind of an asynchronous read, and that might be okay. And then there's this thing in here about interrupts. Every time it's done with a conversion, it can interrupt the computer and tell you to go get the sample. And you can enable the interrupt. So these are more exotic and interesting things to study, and we can do that later. But when you look at my code, kind of ignored all of that in my loop, and you can see it here. All I did was I said, well, I'll do an analog read. It'll take as long as it takes. I don't care. And then when I'm done, I'm going to do an analog write, and I'm not going to have it do conversions in the background. I'll just do another read and wait for it to come back. So I took, you know, the lazy man's approach to programming it here. But if I was going to do it upright, I'd have it convert in the background based on an interrupt, which then tells me to do the read and do the processing. And that actually is useful and interesting code, but it's a little bit harder. So there you go. That's question, probably too much detail for question 14, but I think it was useful for you guys to see the thinking behind it. Did that answer your question okay? Who's still confused? All right, we're going to proceed then.
Yeah, we're all right. Thank you. Sorry about that. I was muted.
So now here comes another bit flippy kind of thing, and it's it's a dirty little secret of the multiplexer. You know, what happens here is your ADD converter, it looks like you got 6 inputs, right? When you look at the chip, here, let's see, look at the chip. Here's the chip. What do I see? ADC 0, ADC 1, ADC 2, ADC 3, 4, 5. Looks like I got 6 inputs, analog inputs 0 through 5. That's great. Guess what? I don't have 6 A to D converters. I only have 1 A to D converter. Instead, what I have is 1 A to D converter and a multiplexer, an analog multiplexer with 6 inputs. And I have to choose which of the inputs are going to be active. And that's going to impact my sample rate, my conversions, perhaps even my overall dynamic range. I may not be able to use all 10 bits worth of A to D conversion input if I go through all of these inputs. And so that, and here's the other thing. It looks like there's a 2-wire interface being reused for input 4 and 5. So if I want to use 2-wire input, it will conflict with ADC inputs 4 and 5. So that's no good. I probably don't want to use those first. So there's a couple of problems here. You know, you can see this right here with the chip. This is a dual inline package. Most of the times, unless you're using the shop-based Arduino Uno, the one in the lab, you're not going to be using you know, a DIP. You'll use a quad leaderless chip. And it's a surface mount device. So then what you look at in here is you say, geez, it looks like 6 A to D converters, but it's not. It's multiplexed. And so I have an A to D converter multiplexer. And that's the reality of having to program this thing. And so when you want to use the ADC and you have to set up the analog to digital converter multiplexer, let me zoom in just a little bit, make it just a little bigger. There. Now all of a sudden, there's a whole bunch of interesting bits that need flipping. And, you know, the bits are kind of unrelated. First, there's the multiplexer, and I get that. You gotta set the mux up to choose which A to D converter you want to use as input. But then there's these other things, the references, the ADLAR, another reference which is intermixed with the ADLAR, and why did they put it here and not over there, or arrange these in order? I don't know what the heck they were thinking, but somehow this reference got moved relative to the other two, and you'd think they'd group these together, but they didn't. Don't know why. And it says here, I can use an external analog voltage reference when doing A to D converters. In other words, let's assume for the moment that you want to jam out with your guitar. Right? Well, your guitar is not outputting a voltage from 0 to 5 volts. So you run it through a preamp. Well, it's still not outputting a voltage from 0 to 5 volts. In fact, you're lucky if you can get plus minus 1 volt peak to peak. So A to D converter, well, it wants 0 to 5 volts. Unless you set the voltage reference up. If you set the voltage reference up to an external voltage reference, then you can let the A to D converter float relative to the power supply of the Arduino. That's kind of that's like a real electrical engineering kind of consideration because guitars don't output 0 to 5 volts. The real world is not 0 to 5 volts. It's just not. And so you have to consider whether or not you want to use an external voltage reference or the internal voltage reference. And so we've got a nice internal voltage reference, which saves us a whole pile of work. And we can just set this up so that it goes 0, 1, 0 for refs 0, 1, and 2. But look where you have to put them. They go 0, 1, and then 2 is way the heck over here. And I look at that and I go, what the heck were they thinking? It's indefensible that they should have done that, but that's the way it is. It is what it is. So yeah, you're spreading the bit sets around, and you can see how the bit patterns will change the behavior. So I can have an external reference, or I could have an internal reference. The external reference can turn the internal reference off and use ADC 0. Or the internal reference can be at 1.1 volts or 2.56 volts, maximum peak-to-peak voltage. And if you want to let it float, that might be a problem. So you probably have to put in an op amp and condition it so it ranges from, 0 to 2.56 volts. You really have to condition it properly, or else you're going to get bad numbers. You won't get a good digitization of the signal. So now that we've covered that, consider the following code. ADC MUX 0110 0000. According to the reference manual, the bits for the MUX should look like this. So here they are. Right? So what is this saying? 0, 1, 2, 3, 4. It looks like bits 5 and 6 are set to 1. 0, 1, 2, 3, 4. Here's bit 5, and here's bit 6. So if bit 6 is 1, then that means reference S1 and reference S2 are set to 0. And so what that does is it gives me a number that's going to be 0, 0, 1. Right? So now looking at 0, 0, 1, it's an external reference voltage at PB0 with internal reference turned off. And then the other thing it's doing is it's setting ADLAR. And so if I go in through here and I want to look at ADLAR, I don't think it's being described, but there it is, 001, internal reference 2.56, ADC channel 0. So that's the selection I would select. And that's how you read that stuff. This makes for, I don't know, complicated code, bit fiddly code, and you'll see things that just don't make any sense to you in the code. And they won't make sense unless you either carefully document what you're doing by writing in the comments, or you go back and start reading the hardware manuals. Because if somebody just says, you know, what's the name of this register here? 80 mux equals. And then they say, you know, something in binary like B010 or B equals, I see. He'll say 80x mux equals B0110000, semicolon. And you're like, what the heck is that? What does that mean? And the answer is somebody didn't document what the ADC 80 mux selection register does in terms of its bits within the code. And often that won't happen because it's cumbersome to document all of this stuff. You need pictures. And so that's where you have to actually read the book and learn how to use the hardware. If there's anything this course tells you, it's that you can't program hardware unless you read the data sheets. And that's just the way it is with hardware. Did that kind of answer your question about question 15? Was that helpful? I gotta somehow bring up the I had a very nice chat window here, but it's not. I don't know why I can't see the chat window. Where's the chat window? Well, life in the big city. Chat. Nope. I don't know why the chat window isn't showing.
That's okay. I think that answers most of the questions.
Good, good. So
it's just reading the table. That's all.
Yeah, I mean, this is not easy stuff. No question about it. I mean, you really have to kind of, once you get used to it, it's not too bad. So here we are again in the same register layout, 0, 1, 1. So let's see, how does this work? 0, 1, ref 0 is 1, ADLAR is 1, and then 0, 0, 0, 0, 0. So it looks like we're going to be doing ADC input 0. And looks like we've got some more bits flying around here. This is question 16. Consider the following Atmel documentation. Image result for AD MUX Arduino ADLAR within the code. Looks like ADLAR is set to 1. And so what does that buy me? ADLAR equals 1. Most significant bit comes first. ADL, most significant bit. Did this answer the same question twice? What's the difference between the first one and the last one? Wait a minute. Is there a bug here? hold on. This doesn't make sense. Does this make sense? Most significant byte comes first. And the next one is, oh, ADLAR 0, most significant byte comes first. We know that's not what it is. We know it's a 1. This should say least significant byte comes first, or 0, least significant. Oh, there's a bug. There's a bug in my question. Okay, so let's fix that right now. Sorry about that. I can see where that would be.
Doesn't it mean the same thing though? If the
Yeah,
most
it does. I
significant
mean,
byte
it's the
comes
same. It's the
last?
same question. Sorry about that. So it
No,
looks
no,
like we've got a bug in the
I'm saying
question.
that you're fine.
Oh, do you think it's fine?
Yeah, because you're saying the most significant byte comes last, which means the first one comes first. Is that not the answer?
Let me go back to the homework. Homework number. We're doing homework number 4, right? No, 5. 5.
Yeah, number 16.
All right. So let's edit the test. Go right through to number 16. Most significant byte comes first. ADLAR1. That's true. But this should have said least significant. Oh, comes last. There it is. This is, for some
Yeah.
reason, I missed the first and the last part. So they are different. I thought they were both saying the same thing, but they're not.
No, they're different.
We know ADLAR is 1, so that eliminates the other 2, where ADLAR is equal to 0. And then the question is the most significant byte first or is it last? That's the question. So you have to refer to the ATML documentation on ADLAR and decide if it's going to be first or last. And one thing you can do, I mean, if you're, ADLAR, I think you can use the Google on that one and then maybe type in Arduino. And now you could ask if it's first or last. See if that helps you. And certainly someone is asking the same question. So you could read about those. Or you could get the ATML documentation. That's actually very convenient. Let's just see if we've got something in here. Oh, somebody summarized this nicely. Is ADLR in here? Ah, here it is. Let's zoom in a little bit. And just kind of, there it is. Left adjusted for 8-bit results or right adjusted for 10-bit results. So if you just want to use 8 bits of the thing, you could do ADLAR 1, and you're just using the 8 most significant bits that are being read in. So that's a nice way to speed things up a bit. You can tell the register when to stop with the conversion and notify you. And here are the mux settings, and they're kind of what you'd expect. In binary, it's 0, 1, 2, 3, 4, 5. For Arduino inputs, 0, 1, 2, 3, 4, and 5, respectively. If you get to a Mega 2540, you actually have a lot more Arduino inputs. I've got one right here. Just a minute. I don't have a camera, but I can see the inputs on this guy, and they go from 0 to 0 to 7. So he has 8 inputs. But I imagine you could find an Arduino variant that has even more. Oh, wait a minute. Oh, I see. It keeps going. Analog in is 0 through 15. So he's using all the bits on the Arduino Mega 2540. You've got 16 inputs. So that's cool. A0 through 15. in the Arduino Mega variant. I don't know if you've seen an Arduino Mega. It's just like an Arduino Uno, only on steroids. I'll just quickly show you. This is the Mega 2540, and I'll get you a picture. There. So here's the Mega. You can kind of see it's quite a bit larger, and it has. I wonder if I can zoom in on this. Can you zoom in on these pictures? There it is. Now you can see it. Analog in A0 through A15. So when you get to the Mega, and it's not all that much more expensive, then you'll have actual 16 inputs for your analog multiplexer. And you can kind of see why the pin mapping has changed too. And it's got more serial outputs. And it's just kind of an all-around bigger chip. And so we can learn more about that if you want to Google it. They're charging, well, I mean, that's an insane price, $40.30. I mean, that's more than a Raspberry Pi. I mean, I don't know why anybody would want to pay that, but you can certainly find them way, way cheaper on eBay. I think Chris found one for, Chris, are you online here? How much was it? I don't see you here. Chris is missing in action. Oh, but anyway, he sent me an email. He said, "Oh, I found an Arduino Mega in a form factor not like this, in a tiny form factor, and it was, I think it was under $3, some insanely cheap price. So you can find these inexpensive. Anyway, there you have it. That's good. We got the SPI DAC and the A to D converter here thing going, which is pretty nice. What else? I don't mind spending a little time going over homework 5 because I think it's really educational for us to do that, especially because there's a lot of, I'll say, subtlety in the homework. How is this form factor with Zoom? Is this okay for people?
Yes, this
Yeah,
is
I think
fine.
it works.
Good. All right. So then we'll try this again next time if that's all right. We'll go to homework 6. Let's see what we can do with any more questions we have for homework 5. I'm just going to scroll through this real quick and see if you guys have any questions. So we got up to question 16, I think it was. And here's question 16. Let's see, what do we got? Question 17, okay. Consider the following code. Timer PWM fast mode to set fast. This is pulse width modulation. So this is a timer control register, and it's being set according to this to prescaler 1. Here's another timer control register, and it's also being set in accordance with some kind of documentation. And then there's this other register, WGM, and he's setting the bits on that to 0101. And then it says here, there's some other bits which are being set to 10, and some other bits which are being set to 10, and here comes some more bits which are being set. And oh my God, it's so complicated. I don't understand what's going on. Capture, compare channels. So now here comes some sort of a hardware diagram. Right? What is this doing to me? Oh my God, so complicated. And it says it generates an intermediate waveform which is used for reference. So what are we looking at here? This looks like a 2-to-1 multiplexer, and when you set the bit, it takes out that side, otherwise it takes out this side, and the only thing it does is it puts an inverter in there. That's all it does. And then this looks like some kind of a timer control register with perhaps 3 bits in it, 0, 1, and 2, OC1M, I guess they're calling it OC1M. Did we see that before? I don't know if I saw that. And then there's this reference over in here. And for some reason, I cannot copy and paste out of this thing. I do not know why. Gosh, that's annoying. Oh, and here's documentation. So the documentation's already in here. That's great. And so here it says COM1A1, COM1A0. And so these are 2 bits. And when you set 00, it disconnects pin OC1 from the timer counter 1. What the heck? Timer counter 1. Let's just look. COM1A1. Do we see that in here anywhere? He's saying disconnect pin OC1 from timer counter 1. Do we see pin OC1 in here? OC1. Here's pin OC1. And this looks like a timer counter register. I don't see OC1 anywhere else. Oh, here is OC1 coming out of here. And this says CC1E time X CCR CCER. So what's he talking about here? Here's PWM disabled. Counter is 8-bit, 9-bit, or 10-bit PWM. And then here's a timer control register. And it looks like that image got mangled a little bit. And then it says input noise, capture noise canceller. If set, the noise canceller on ICP pin is activated. It will trigger the input capture after 4 equal samples. Complicated, right? I know computers are hard, but couldn't they make this a little easier? So input capture edge select. Input capture edge select 1, 0. When cleared, the contents of the timer counter are transferred to the input capture register on the falling edge of the ICP pin. If set, the timer counter is transferred to on the rising edge of the ICP pin. Clear counter. You really have to read this stuff, all these words. Oh my God, who can stand it? And so otherwise it's going to be corrupted and it won't work. And they put all this stuff in here. And there's a divider. It's just building a counter, right? Output compare register, OCR. Ah, so that's what it stands for, OCR, output compare register. Permanently compared to the timer counter when both match, we compare the match. It's inputs every time. Input capture register is used to measure the time between pulses of an external capture pin. So the timer can be used as an internal timer or an external timer. If it's used as an internal timer, we can scale what the timer is responding to, and then it can generate an interrupt. So the whole point, what's the point of this? You're going to create a timer that's going to generate an interrupt that's going to allow you to output a signal to the pulse code modulation output system. Let's see why we would need something like this. Which of the following are true? I got 2 minutes. I'm going to do a real quick thing, but I don't know if I have time. I was going to show you a Tinkercad thing, but let's not do that yet. Which of the following are true? The timer